Let's consider now the temperature dependence upon the rate constant. So this is given by the Arrhenius expression. And it says that the rate constant K is equal to a constant A times e to the minus EA over RT power. So this is how the rate constant K depends upon the temperature T. We have this E sub A, which is the activation energy for the reaction. T is the temperature. R is the ideal gas constant. A is called the frequency factor. And K is our rate constant. So the frequency factor has to do with how efficient collisions are at initiating a reaction. So do we have to have on average 10 collisions before we have a reaction, or is every collision initiating a reaction? So this is embedded in the frequency factor. The activation energy is a barrier we need to overcome in order for the reaction to proceed. So in chemical reactions, we're going to break bonds and then reform new bonds, and it takes energy to break bonds. And so this activation energy has to do with how much energy is required to start the bond breaking process. So let's look at the activation energy in a little more detail. So we have reaction coordinate. So we have, say, reactant and products. And this is the energy of the reactant. So this is energy on the scale. And this is the energy of our product here. So we have the energy of the reactant, energy of the product. This is called a potential energy surface. It's just the energy as a function of the reaction coordinate between reactant and product. And here at the very top is called the transition state structure. So we have reactant going to product, so we're changing the molecule. So we're going to break some bonds and then form new bonds, going from reactant to product. And at the very top of this energy curve is the transition state, and the activation barrier is the energy required to go from the reactant to the transition state. So this is the activation energy for the reaction. So in order to start breaking bonds, we need to input energy into the molecule. So once we hit the transition state, then it's downhill to products. So this, along the reaction coordinate, the molecule will spontaneously rearrange to give products once we pass through the transition state. So if the activation energy is very large, then it takes a lot of energy to get over this barrier, so the reaction will proceed slowly. If we can lower the barrier, then the reaction can continue, or the reaction will proceed more quickly. Now a catalyst has the ability to lower the activation barrier. So if we have a catalyst for our process, then we can lower the activation barrier going from reactant to product, so the reaction will occur more quickly. So a catalyst lowers the activation energy for the reaction. For using the Arrhenius expression, The frequency factor is sometimes difficult to calculate, and we'd have to measure it experimentally if we wanted to get that. So if we take the ratio of the rate constants at different temperatures, the frequency factor will cancel. So say I start at temperature 2, and so I have the rate constant at temperature 2, and I divide by the rate constant at temperature 1. So this rate constant at temperature 1. The frequency factor will cancel out, and if I combine the exponentials, I'll get this expression. So now I have the ratio of the rate constants is equal to E and to this power. So I can either, if I know the two temperatures and one of the rate constants, I can solve for the other rate constant if I know the activation barrier as well. So I have 1, 2, 3, 4, 5 things in this reaction. The two rate constants, the activation barrier, and the two temperature. If I know 4 of those, I can solve for the 5th.